Right, now we're moving on to the graph of y equals tan x, and I'm sure you're looking at this and thinking that it is vastly different to the sine graph and the cos graph. Let's have a look at where it is similar. Well, we've drawn it from minus 360 to 360. So that is a similarity, and once again, you would be particular and make all of these degrees with a 0 degree. Now, that is where practically the similarity stops. Can you see how the tan graph is actually stretched way beyond the limits of 1 or minus 1? But it kind of continues up to the sky and down as far as it wants to go down the bottom here as well. All right, so it looks like we've got some kind of a difference as far as the amplitude is concerned. So that's one thing that's different. The next thing, if we have a look at the graph, can you see that we've got these dotted lines at minus 90 and 90, again at 270, and again at minus 270. Now what I'm going to do is just scroll down and keep part of the graph so that we can introduce some of the language. Now the graph is 0 at 0 degrees, then at 90. Let us have a look at what happens if we put in the tan of 90 into our calculator. So we go to our calculator, we're out of the f of x mode, we're just going to put in the tan of 90 degrees. All right? Now can you see that it says math error? Now that isn't that you've made a mathematical mistake, but it means that the calculator is unable to work out the tan of 90 degrees. Now that is because when we work out the tan of 90, we land up taking, remember tan, all right, of any angle is the opposite over the adjacent. And at 90 degrees, the adjacent value is equal to 0. Now, you are aware that if we take a value of 0 and we divide by 0, then we would get something which is undefined. And the only way that the calculator can caution you and say you've got something undefined is it then tells you that you have got something called a math error. So you haven't made a mistake. It's the calculator saying, we can't work this out. Now, if we work out the tan of 90, we get a maths error, and 270, and minus 90, and minus 270. And those dotted lines that we have there in the graph, those have a special name, and we put them in vertically at 90, 270, minus 90, and minus 270, and those lines are called asymptotes. And yes, you do have to know that word. All right, they come up again in other algebra graphs, and the spelling is also quite important. It's an asymptote. So we've got our asymptotes, 4 of them in this particular region. Now let's have a look at what we would talk about as far as the period is concerned. Now can you see that a tan graph actually basically consists of this passage here coming from negative infinity, very close to the asymptote. It then travels all the way up, and then it travels for the sky. So one of these tan pieces, all right, it's disjointed. One of these pieces looks something like that, and it's bordered on both sides by an asymptote. Now, can you see that that has happened within a span of minus 90 to 90? Now, 90 minus minus 90 gives me 180. The next wiggle happens between 90 and 270. Can you see that that is a span of 180 degrees? So this is the first very, very important difference between sine, cos, and tan. And that is that for the graph y equals tan x, we have a period, all right? And remember, a period is how long it takes to do a pattern. And here our pattern takes only 180 degrees. All right, and this is vitally important compared to the sine graph and the cos graph. Right, let's go and have a look at some more interesting facts about tan. Right, between 0 and 90, that is actually our first quadrant, and tan is positive in the first quadrant. Then it comes up very close to this asymptote. It doesn't ever hit it, but it keeps on going higher and higher, and it just keeps on scooting to the left of that asymptote. Then, let's have a look at what happens if we take tan of 91 degrees. Can you see that it's negative, and it's very negative? So what the graph has done is it's got very big, then it's become undefined, and now at 91 degrees, just to the right of 90, it's down at minus 57. So we're coming from negative, and then we start getting positive. This is our second quadrant, and then we head for the skies again. So that is what is happening, is it's positive, negative to positive, then it breaks again, it's undefined. So can you see that it can't flow? It's not continuous. So only for 180 degrees can you not move your pen. Can you see it's continuous through that piece? Then you've got to jump, and you've got to start again coming from the bottom up to 360. So what important things do we need to know? First of all, we need to know that the asymptotes is the name for our dotted line. Next, we need to know that our period is 180. So, of course, this leads us then into what is our amplitude. All right? And for me, this does not have an amplitude. So I'm saying that it does not exist. All right? If you said that the amplitude was infinity, all right, that's also in a way correct, because can you see the height is infinity? It keeps on going forever, but what is infinity? So we can't really measure the amplitude of a tan graph. However, we can say that the range of a tan graph is going to be y is an element. It goes from negative infinity up to infinity. Now, if you'll recall, when I did the range of the sine graph, I used square brackets. But remember that infinity is a concept that we cannot include. We do not know how big infinity is. So that's why we use round brackets. And notice, too, that I go from the negative infinity, the smallest, up to infinity, which is the biggest. And the only other thing that we really need to comment on is, again, that every 180 degrees, because of my period, can you see every 180 degrees, I'm going to have what is called an X cut. Right, now, if I was drawing this using my calculator, and I put in my values 0, 90, 180, 270, 360, let's have a look at what happens on the calculator and how I need to adapt my introduction in terms of what I give the calculator to work out. So again, I'm going alpha x, so I'm doing tan x equals. If I'm starting at minus 360 and I'm ending at 360, now if I go in steps of 90, I'm going to get 0, then it's going to bomb out. Then I'm getting 0, then it's going to bomb out. So in fact, I want to go in steps of something a little bit more useful to me, which is 45 degrees. All right, and it now gives me minus 360 must be mapped with 0. Then at minus 315, halfway between here, I must plot that with 1. Now, can you see that that is going to link up with 1, that point there? So that would be a very important point to plot. Minus 270 is giving me error, so that's my asymptote. Then let's just have a look at another couple. Minus 225, halfway through this block, I'm again going to plot it with minus 1. So if I now clear this, What is important is I'm going to plot this point as a stabilizing point and then join those up. Then I'm going to plot minus 2 to 5 as a stabilizing point, and I'm going to join those up. Halfway between here at minus 135, that would match with 1, and I would join that up. So it is important at 45 to plot it with 1 again and to join that up. You can't just go naught and head for the skies. You must have some kind of stabilizing point, and it's going to be 45 halfway through to 90 together with 1 in your normal tan graph. So that is exactly what happens when we draw the graph of y equals tan x. But of course now what we have to have a look at is what happens when we draw the graph of y equals 2 tan x, because that's what we did when we looked at the sine graph and the cos graph, is the actual effect of the 2 in front of the tan. So as you can see, the blue solid graph is our graph of tan x. You can see that its period is 180 degrees, and you can see where those dotted lines or the asymptotes lie. Now if we have a look at the pink graph or the dotted line, can you see that it's very much the same? Its period is exactly the same. It still stretches across from minus 90 to 90, taking up 180 degrees. The only thing is that it is sharper or steeper. So what we can see is that the difference is that where our point here is going to be the point of 45 degrees matched with 1. In our pink graph, it is going to actually just be 45 matched with 2. So remember that the 2 in front, in fact, affected the amplitude for the sine graph and the cos graph. But that was stretching something that was 1 to something that became 2. Now our amplitude, the graph goes up to infinity and down to negative infinity anyway. So the only effect of the 2 is that it gets there a little bit quicker. And that is why it is so important for us to plot the stay points so that we can see that the one is a bit gradual and the other one is steeper. Of course, the next thing that we looked at with our other 2 functions, sin x and cos x, was what happens if we put a negative in front. So what we are looking at here is the effect of putting a minus in front of the tan x. And as you can see, the blue graph is our original, and our pink graph is our minus tan x. Now what I would like you to notice is that just like the minus had the effect in the sine graph and the cos graph of flipping the graph, actually taking it and reflecting it across the x-axis, that is exactly, guys, what is happening here. So can you see that this bit here actually gets reflected to that piece there? All right? And likewise, if we take this piece here, it gets reflected to that piece there. So where we had a point of 45 with 1 on the original graph, we now have a point 45 with the y value going to minus 1. So can you see how this has just been reflected across the axis, and so where before it went up to 1, it now goes down to minus 1. So the effect of the minus in this particular graph is just to reflect the graph across the x-axis, which is exactly the same that happened with our sine graph and our cos graph. Okay, so guys, the only other thing that I need to mention is that when we are taking the tan x graph and the minus tan x graph, can you see that whether it was the original graph or the reflection, it went down to minus infinity and up to positive infinity. So where the range is actually inspected, before we would have said that y is an element of real, or we could have said that y actually spanned from negative infinity to positive infinity. Now that is exactly the same for both of these graphs. It hasn't been affected at all, because originally it went all the way down into the bowels of the earth and all the way up into the heavens, and that hasn't changed. All that's happened is that this particular wiggle has changed and is reflected across the x-axis. Right, I hope that that is very clear, and we're now moving on to the next functions.